Let's go ahead and move on to projectile motion. Now, before we actually get into projectile motion, I want to talk very briefly about the derivation of the equations of motion. So if you have taken a physics class, then this is going to be very familiar to you. And you are more than welcome to go ahead and fast forward until you get to the screen that has the baseball player on it. But if not, this is some useful background information on where the equations that we're going to be using come from. Now, it's based on a couple of basic definitions. The first one is this definition of acceleration. And acceleration is just the change in velocity over the change in time. Anytime you see that little triangle, that's just the Greek letter delta. And in math and science, delta represents change. So acceleration is the change in velocity over the change in time. Now, change is just whatever your current velocity is, let's call it v, minus your initial velocity. This is sometimes referred to as v initial, or more commonly v naught. N-A-U-G-H-T. Naught is just an archaic term for zero. So this is v sub 0 or v naught, and it just means the initial velocity. So your change in velocity is just whatever your current velocity is minus where you started. Same thing with time. But if we're talking about initial time, it's very helpful just to consider, let's just call initial time 0. That way we don't have to put this t naught term anymore. So we can just say v minus v naught over t. So acceleration, v minus v naught over t. And it's important to point out that we are going to go ahead and assume that it's constant acceleration. If we allow acceleration to change over time, then these formulas don't really work out all that much. So we're going to go ahead and assume constant acceleration for all this process. Now, if I go ahead and take this formula and solve it for v, move the t over, move the v naught over, I get this handy-dandy little formula, which is velocity equals acceleration times time plus your initial velocity. So if I wanted to know the velocity of an object, if I know that it's constant acceleration, and I know what time it is, and I know what velocity it started at, then I can tell you what its current velocity is. Now, just like acceleration is defined to be the change in velocity over time, velocity is defined to be the change in the change in position over time. It's common to use the letter S to represent position because some of the other letters that we use for position, X and Y, are already being used elsewhere. The letter D can go either for distance or displacement, so I don't like to use the letter D. I like to use the letter S just because I like to use the letter S, because apparently using the letter P for position was just too obvious, so let's go with S for no reason at all. Now, just like we did before, I could say change in S over change in time, or I can think of another way to describe velocity, and that's with average velocity. If I wanted to average two velocities together, that's just a matter of adding them together and dividing by 2. Well, because we are assuming a constant acceleration, that was key to this problem, that means the average velocity and the instantaneous velocity, the velocity at any given point in time, are going to be the same. So I can go ahead and just set these equal and solve based on that. So I can move the delta t over. I've got v plus v naught over 2 times delta t. I can remember that v is really at plus v naught. Plug it in, so I've got at plus v naught over 2 times delta t. And that's going to be 2v naught. Separate the fraction into 2 separate parts. I've got at over 2 plus v naught. Now, this is the point where I realize, well, delta t is really just t, just like we did in the acceleration problem. Delta t, t minus t naught, assuming that t naught is 0. It's just t. If I were to distribute that t across, I would get t squared and v naught times t. And right here we have our position equation. Now, this really should say delta s still. I took the delta off the t and accidentally took the delta off the s as well. This just represents the change in position. If I want to make it just straight position, that's just a matter of detaching. So that delta s is really s minus s naught. Well, if I move the s naught to the other side, I have my position function. All right, position given constant acceleration is 1/2 at squared plus v naught t plus s naught, where s is position, a is acceleration, t is time, v naught is your initial velocity, S naught is your initial position. This handy dandy little formula is going to be used over and over and over again when we are talking about projectile motion, so it's useful to memorize. Now, let's use that in terms of projectile motion and two-dimensional parametric motion. So imagine someone's throwing a ball. When he throws that ball, he's throwing it at some initial velocity. That velocity is going to change over time based on direction, but initially he's going to throw it at a velocity at some angle with respect to the horizon. So that is your given information. You're going to know how fast he's throwing it, you're going to know the angle, and you're also going to know the height of the ball. And I can use all that information to create a set of parametric equations to describe the path of that ball. And I can use that basic position function in order to do it. Now, velocity, your initial velocity, think of that as a vector. Alright, so you've got v naught, which is the magnitude, and then theta is your direction. Now that vector can be broken into two components, your x component, so I just called it v sub x, and your y component, v sub y. Now remember, v sub x and v sub y represent your velocities in the x and y directions. Because if you think about it, when you throw an object, the position in the x and the position in the y have nothing to do with each other, as do their velocities have nothing to do with each other. As you're traveling from left to right, you're just going to travel along in your merry way, but you're also going to be traveling vertically up and down, first up and then down, but that's not affecting how it's traveling from left to right. So we can separate it into those parametric equations using their velocities. Now, of course, v sub x is your x component, and we can think about what we did with vectors to figure out your velocity in that direction. Again, it's just your magnitude of the vector times the cosine of the angle for Vx, and then magnitude times sine for V sub y. Alright, now to get our x direction, or our x position equation, we'll start with our standard formula. But here's another thing we have to realize: as we're traveling from left to right, it's not accelerating at all. It's just traveling on its merry way at the same velocity forever and always. It just travels in the same direction without changing velocity. Now, of course, we're ignoring any friction due to atmosphere or wind or anything like that, just like we like to do in physics classrooms. Then we get out to the real world and everything's up in the air, literally and not literally. But in the x direction, there is no acceleration. You can't force it to go faster once it's left your hand. Alright, so we can go ahead and get rid of that acceleration term because that's going to be 0. And based on where I put the xy plane, your initial position is going to be 0 in the x direction. So in the x direction, the only thing that really matters is your velocity in the x direction and your time. In other words, distance equals rate times time. So v sub x is v naught cosine of t, and what we have there is our x position equation. We can do the same thing for y, but this time acceleration actually does matter because, of course, on planet Earth we have something called gravity, which is causing everything to accelerate straight down at a rate of negative 32 feet per second squared. Let's go ahead and fix that. Alright, now of course if you're in meters, then it would be negative 9.8 meters per second squared. But if we're sticking with feet, it's going to be negative 32. In a math class, we typically stick with feet. In physics, you'd switch to meters. So I can plug in negative 32 right here. V sub y is going to be this guy right here. And y naught, and y, the initial position, is just going to be the height of the ball. So right here we have our x and y parametric equations of motion. We're going to use these in order to map out a projectile path and make some predictions. Alright, Jebediah hits a ball at 4 feet above the ground with an initial speed of 135 feet per second at an angle of 25 degrees with the horizontal. So here are some questions that we want to address, but before we jump into that, we need to figure out what the equations are, and I'm going to use those two equations that I just derived in order to do this. So I've got 4 feet above the ground, my initial height, my initial velocity, and the angle at which that velocity occurs. So let's just take that information. I'll go ahead and plot it in the picture and write my equations. So remember, x is just velocity times time. Velocity in the x direction means I need to slap a cosine in there. So V naught is 135, cosine of 25. So there's my x equation. I can do the same thing with y. Again, acceleration is always negative 32, so you can always go ahead and start with negative 16t squared. Velocity times time, slap a sign in there because it's in the y direction. And then y naught is going to be your initial position in the y direction, which is 4. So these are the two equations I'm going to be using that can map out this particular path. So everything I do is going to be based on these two equations, so we'll want to keep those handy. Alright, part A says, what is the height of the ball after 3 seconds? Notice keyword height. I am talking about a height, which means I am only talking about the y component of the path. The x component has nothing to do with height. It doesn't matter how far you are from the initial point. All that matters is how high I am, so the only thing I need is the y equation. And the question is at 3 seconds, so let's just evaluate y of 3. So it's just a matter of pulling out my calculator, typing in my y equation with 3 plugged in for t, and I get my answer of 31.160 feet. I didn't need the x equation at all because, again, x and y are completely independent of each other. Question is height, I just need y. Part B, how far has the ball traveled after 3 seconds? When it says how far has it traveled, that's implying how far did it travel along the ground, in other words, in the x direction. So just like part A, I only needed the y equation, part B, I only need the x equation. So just like I did before, plug in 3 for t in the x equation, 367.054 feet. So at 3 seconds, it's 367 feet downwind, and it was 31 feet high at that point. Now notice it doesn't tell me whether the ball is rising or falling at that point, so it could be 31 feet on its way up, or it could be 31 feet on its way down. Based on the context, I'm 367 feet away. I'm going to guess it's probably on its way down by now. Alright. Moving on, what is the maximum height of the ball? Now again, I just mentioned on the last step, I'm assuming at 367 feet it's on its way down. So it's probably reached its height prior to that 3 second point, but I can't be sure. But again, we are asking about maximum height. Alright, height again is the y equation. The only thing I need is the y equation. So here's the point where I can realize, well yeah, I'm doing a parametric equation, but I really don't need both parts, just one part. So I'm going to go ahead and answer this the same way I did way back in chapter 2 when I was asked for a maximum value. I want the y value of the vertex. A maximum value is the y value of the vertex, specifically the vertex of the y function. So to get the vertex of the y function, I'm going to remember that handy dandy little formula, negative b over 2a. Negative b over 2a would tell me the x value of the vertex. Now of course, instead of calling it an x value, we're just going to call it a t value because that's the letter this equation happens to be using. Not x in terms of the x equation, x in terms of the input value, which is t. So negative b over 2a, the b value is this whole guy right here, a value is negative 16. Type it in the calculator, I'll get about 1.782. So at roughly time 1.782, the ball is going to reach the top of its arc, which that actually confirms what I said in part B, that the ball was probably headed on its way down after 3 seconds because it reached its peak at a little over 1.5 seconds. So at time 1.782 it reaches its peak, but that wasn't the question. The question is, what's the maximum height? I want to know the height of the ball at that point. Again, don't retype things in your calculator. Go ahead and store that for one of your alpha letters, and then instead of typing in 1.782 for the height function, go ahead and type in a for the height function, and you should get roughly 54 feet. So the maximum height of the ball is 54 feet, and it occurs after about 1.5 seconds. Part D, how long is the ball in the air? Well, it's in the air for as long as it's not on the ground. So in other words, instead of asking how long is the ball in the air, I could ask when does the ball hit the ground, which would answer the exact same question. But now it kind of gives me a little bit of a clue. When does the ball hit the ground? Well, that's when the height is 0. So in other words, y equals 0. Set your y equation equal to 0 and solve. Now we could do this the fun way of solving, well, I wouldn't use factoring because there's no way I'm going to get that 135 sine and 25 in the middle, so I could just use the quadratic formula to solve this, or I could use my graphing calculator. Now again, this is a parametric equation originally, but I'm not solving a parametric equation, I'm only solving the y equation. So what I could do is go ahead and graph simply using my y equation. So let's pull up my calculator. Alright, so I'm going to go ahead and graph using only my y equation. Now, right now my calculator is still in parametric mode. I don't need both x and y, I only need one equation at a time, so I'm going to go ahead and put it back in function mode before I graph this. I'll go ahead and graph negative 16 fake t squared plus 135 sine of 25 times t, and before I type, actually let's go ahead and type in plus 4. Before I graph anything, I'm going to remember my calculator was in radian mode, yet this question is a degree, so let's go ahead and fix that real quick. Alright, and before I graph it, I'm going to go ahead and adjust my window. Certain things I've already discovered is that the maximum height was somewhere around 50, and that maximum height occurred after about 1.7 seconds. So I'm going to adjust my window to accommodate for that. X represents your time. So let's go ahead and start at time 0, and let's go as far as time, let's only go 5 seconds down, because it was already on its way down after 3 seconds. So just give it a couple of extra seconds, it'll probably hit the ground by then. If not, we'll go ahead and adjust that. Alright, and then for y min and y max, I like to have a little bit below the x-axis just to make sure that nothing gets blocked by anything on the bottom of my screen. So I'll go as far as -2, which is going to be 2 feet below the ground, and I'm going to go as high as 60 because I know the maximum height was somewhere in the 50s. So let's graph it and see what happens. So there's the path of the ball, maximum height, and then it lands right here. Alright, so I just need to know what time it hits the ground, so I'll just use second calc. I'll find the 0. I'll move that cursor so that it's on the left and right of where I think it hits the ground. I'm going to use the left and right arrow keys to do that. Now right now I could go ahead and hit enter now because I'm already on the left of the x-intercept, but I like to move it a little bit closer just so my calculator doesn't have to work as hard. Now that seems close enough. I'm only 12 feet above the ground. I'll hit enter. That creates my left bound. Now I need to make a right bound, which needs to be below the ground, so I'll move my cursor until I see some negative numbers for the y value. There's a negative number, which means I'm just to the right of the x-intercept. I'll hit enter one more time. No need to guess, hit enter one more time, and it will give me when it hits the ground at 3.634 seconds. Remember, that's scientific notation there. Looks like a -18. Oh, sorry, no, this just says -1 e to the -11. Which is really -1 times 10 to the -11, which is 0. So it hits the ground roughly at 3.634 seconds, which is exactly what I knew it was going to be. Alright, moving on. Let's move this off to the side. A 20-foot wall stands 400 feet from the batter. Will the ball make it over the wall? So really the question is, when the x position is 400, what is the y position? Because if the y position is 20 feet or higher, it's going over the wall. Well, actually, if it's 20 feet, it's hitting the top of the wall, so it really has to be more than 20 feet. So really, I need to know what is the y position when the x position is 400. Well, in order to figure out the y position, I need to know what time it is. So to figure out what time it is, I'll use the x equation, set it equal to 400, and then solve for t. So let's set the x equation equal to 400, divide to solve for t, and that's going to give me 3.2 seconds and change. So I just need to know the height at that time. So I'll store that in my calculator because I'm not going to retype decimals, and I'll plug that into my y equation. When I plug it into my y equation, I get 19.5-ish feet, which tells me that at that time the ball is slightly less than the height of the wall, therefore no, the ball will not go over the wall.